All right, testing. Okay, cool, that works. All right, cool, okay. All right, let me share the screen. Okay, cool. So today, what we're going to do, just sort of to wrap up the last couple of weeks, today, we're going to talk about concurrency, which will be primarily in Snap. And so the reasoning, the thinking about concurrency, we'll do things in Snap. All of this technically applies to Python, or almost all of it applies to Python and other programming languages. But for simplicity, we're going to focus on Snap. And so today's lecture, Wednesday's lecture will be about sort of the fundamental limits of computing. Those two things are in scope for the paper final exam. That's Tuesday, May 10th. Neither of these two topics will be on the online in-lab final exam next Wednesday. Next week, in terms of lectures, next Monday will be an alumni panel. So we'll have a good group of former CS10 TAs. Some of them have been graduated for a few years now and have been working in industry. Others are more recent graduates. One or two of them might actually still be upperclassmen at Berkeley. I'm not 100% sure what our final sort of set will be. But please do come to that. If you could come in person, that'd be great. A few people will be in person, a few people will be over Zoom. So we'll have sort of a hybrid discussion. And then in 2 weeks during Dead Week, Monday and Wednesday will both be review sessions. I'll be doing one of them. The TAs will be doing another. So you'll have opportunities for both those. Yeah, the in-class final exam will be all Snap. It'll be all Snap stuff that you've learned so far. So building functions, returning functions. It'll basically look like a question on a midterm type thing, except instead of sort of reasoning about it on paper, you'll reason through writing some code in lab. So today what we're going to talk about is concurrency. And this is the idea of how our computers and how our programs handle multiple things going on at once. So in the old days, sort of before all of us around, but computers were there, programming and programs essentially were things that just ran one at a time. Computers were slow enough that you could literally see each individual step happening. They were big enough and expensive enough that you didn't have things like multiple processors. And so you would run a program and you would see it output each step essentially, or as much as you wanted to see the output. And for a while, even if two people wanted to share the same computer, today, we don't really think about this too much, but multiple people can log into the same computer. For the most part, if you log into like the lab machines, you're using an account. Someone else could be logged in virtually to the same computer, even though you wouldn't see their work because they have a different account. But computers all basically had sort of one system. You would have to schedule time on the computer. And so you didn't really have any sort of definition or any model for multiple things going on at the same time. And of course, it turns out that multitasking is an incredibly useful thing to have, right? For us as humans, whether or not it's good for us, we multitask all the time. And what that also means is that our computers probably need to reflect that. While a computer is just running, you may be using the keyboard and mouse or trackpad, whatever it is. That is some input, a signal that needs to be processed by the computer, by whatever programs, by your operating system. While that's happening, it is probably reading and updating data on your hard drive. It's probably doing things like downloading or uploading information over Wi-Fi. And in general, you probably have multiple programs running on your computer at once, right? So right now, I've got like Safari and Zoom, most importantly. The application switcher's not up here, but I have a whole bunch of other programs, which actually, let me quit a couple, so I don't get any notifications. But your computer is really good at switching between multiple things going on at a time. And for the most part, it does this in a couple ways. And this is a pretty simplified model. But if we're switching between a bunch of applications, so I don't have Spotify open right now, but mostly what our computer can do is see if there's some task to be done in some application. Is there any keyboard input? So, or is there any mouse input? If so, move it, reflect that on the screen. Is there some information that needs to be downloaded or shared over Wi-Fi, which in this case, I'm not using Wi-Fi, but is there any network activity? And this Ethernet thing has a little blinking light to suggest that yes, of course, with Zoom, there's a bunch of network activity going on. Record and save it. Now run some of the tasks of an application, switch to another application, run some of those tasks, switch back, and do this repeatedly. And modern computers are so fast that the version of multitasking is actually just take all the things that need to be done, try and figure out some order to do them, and just do them in some order. And instead of doing all of the Zoom tasks at once, because Zoom running in the background is not necessarily an open and shut task, nor is browsing the web, right? It is switching between things, just hundreds or millions of times a second to be able to accomplish what needs to be done. Modern operating systems are really good at doing this. So even though we have multiple processors, multiple cores on our processor, sometimes dozens of them, which we'll talk a little bit about, computers largely still simplify the work of doing multitasking to letting programmers think about doing one thing at a time. And this is really useful because when you're writing a program, you don't have to consider what happens if someone is running Zoom in the background. What happens if they're also watching a YouTube video? Does that affect how my program runs? In reality, it probably does, at least a little bit, affect the time that it takes your program to run from start to finish. But as you write lines of code, whether that's blocks in Snap or lines of Python, you as the programmer don't need to think about it. And you can kind of think about this way, as a student going through life, right? You're taking a bunch of classes, you have a bunch of tasks to do, you're probably only doing one thing at a time. Even if you're sort of actually multitasking, you're generally, what multitasking means for a human is instead of spending an hour just on reviewing the readings for CS10, you're probably spending an hour and a half reviewing the readings for CS10 while watching a bunch of YouTube videos. And what that means is you're going back and forth between paying attention to a video, paying attention to a reading, or something like that. Our brains are pretty darn good in ways that computers are not at sort of simultaneously processing multiple streams of input, but they're also not as good as it feels to us. So a lot of times multitasking as a human is really just context switching really rapidly. And in our programs, it's pretty interesting to see how this works. So this is an early lab, right? If I click on a script, this bug will start dancing, and I can click on this one, and this bug will also start dancing, and they'll sort of go next to each other. And no, thank you, Google Drive. So while stuff is going on, and I can even, if I, like, let's say, we can drag out a one space pressed here and here as well. And so now whenever I hit the space bar, right, there's multiple things going on at a time. And what's really happening is Snap and our operating system are making sure that these sets of blocks, while there are two different sprites, it's finding a particular order to do each individual instruction that we've asked Snap to do. and it is just rotating back and forth between sprite 1 and sprite 2 as fast as it possibly can. And so a lot of the times when we talk about things happening concurrently, at the end of the day, there's still some implicit ordering that happens when we run our code. And so that is one of the fundamental challenges of thinking about things in a concurrent model, is how do we reason about when something happens in that order versus out of order. And unfortunately in CS10, getting to a world where we really interact with multiple processors is pretty difficult. So we're just going to talk about some of the challenges for that. But there are ways of doing multiple computations simultaneously, and we'll have ways of sort of demoing some of the challenges. So in this case, in Snap, if we have two sprites that are animating between each other, we can see those animations. It's pretty clear that both of them are making some movements. Their pictures are changing. One sprite doesn't really affect the other sprite. Now, Snap does have mechanisms to simulate running things in parallel or running two operations at the same time. So in this case, we have two blocks. These are really these are pretty simple blocks that we have here. So one of these is just a countdown block, or excuse me, count up block. It just keeps counting numbers. I believe that's just 1 to 26. And one of them just says the letters of the alphabet. So these two things each say one thing at a time for a few seconds or a fraction of a second. We could actually see here, right? 0.35 seconds. And of course, normally we could just execute one block after the other, say all of our numbers, then we could say all of our letters. Now, what Snap provides us with is this block called launch. In the past, so far we've seen call, right, which will let us take some higher order function and turn that in from some piece of data and actually execute that reporter block. And we've seen the run block, which is analogous to call, but for command blocks. And of course, we could actually just verify that if I duplicate this, it does the exact same thing. What launch does is launch says, tell this block to start being executed automatically, but don't wait before continuing on. So launch will take these two blocks, count up an alphabet, and execute them exactly at the same time. And we'll see what happens. So when I click this, they're going to run both of these at essentially the same time. So take a second or two, and I'm actually going to add, actually, we are not going to do that because this will be harder to see what happens if I add something below. That'll mess up the point. But well, let's just say what will happen here. So if I run with run, right, it runs through this entire block. We'll say all of our numbers, and eventually at the end, it's going to say the phrase done. When does it stop? I guess this doesn't. This goes further on than I thought. So it eventually say done. These two will run simultaneously, but they each say something. So if you haven't thought about what will happen, take a guess. I'm not going to ask you to say what you think will happen, but just think about it for now. And what do we get here? In this case, the sprite is very rapidly swapping between letters of the alphabet and numbers until at this point, it's just counting numbers because there's no more letters of the alphabet. But what is happening there is Snap is taking two blocks that are supposed to happen at the same time, and it's switching back and forth as instantaneously as possible between one and the other. What's interesting is that Snap in this case does a pretty darn good job of figuring out that there's two tasks going on. And so it probably means that the best thing to do is to alternate between the first task, the second task, first task, second task. But we don't necessarily know exactly how Snap is going to handle things. Alternating from one to the other makes the most sense. that seems the most sort of fair, so to speak, that if two programs are running at the same time, they each alternate between their priority. But Snap in its own implementation could in theory choose to do something else. But in this case, what we have is two things operating concurrently. And note that normally, we could see the numbers sort of stay around a little bit longer, but they start swapping numbers pretty quickly. So in this demo, the launch block in Snap lets us run two different blocks at the same time, and Snap just figures out how to swap between them. So when we have when we are thinking about concurrency, one of the things that we're trying to do is figure out how do we handle multiple things at the same time, and does it matter if they end up with this implicit ordering behind them. So in this case, we can normally just click two blocks. We could launch them. In the lab for this week, in the concurrency lab, what you'll also see is using Snap's broadcast mechanism. You've probably used the broadcast block before, but broadcast is a similar type of mechanism that launch does. Instead of taking a higher function, it tells some other script to broadcast some action. If I go back over to Snap and we search for something like broadcast, what you've probably seen is that there's broadcast and there's also broadcast and wait. And these two things exist in the same way that we have launch and run, because they give us control as programmers over the concurrency of our code. So in the lab, you'll basically say, do I want two things happening at the same time? Well, broadcast makes sense. Do I want to execute some script in some other sprite, but wait until I have a result before continuing on? Broadcast and wait is probably the better function to use in that case, because that will wait until that entire script is done. And so Snap is, like many programming languages, gives us the tools to say, do we want things to happen in parallel or do we not? And so we have those two functions. Of course, in general, concurrency is really handy in the same way that we've done a bunch of labs that implicitly use concurrency. You've probably used it in some of your projects where you have multiple things going on at once. In 2048, Snap is waiting to receive key inputs from a bunch of different keys, right? Up, down, left, right. You could click with a mouse. In your final projects, you'll probably have multiple sprites moving at the same time. And the really nice thing is that Snap goes through automatically and just handles all of that for us. So the question is, what happens when things actually should happen in parallel? And in this case, this is, of course, not actually true, but consider someone building a house entirely solo and on their own. It would probably take a lot of time for someone to build a house as a person of one, right? In fact, realistically, with the sizes of stuff that you need to lift and move, you probably actually couldn't do it solo. So in practice, you have a team of people. And if you sort of take a look and think about what's going on in this picture, you have a bunch of different activities going on at the same time. You have some tasks, perhaps, that require something to be done before others. But in this case, we're able to have a bunch of people, in this case, probably a couple dozen in this photo, working together to solve a problem faster than anyone could do on their own. Of course, we have to ask the question, if we had a team of 100,000 people building a single house, could they do it faster than a team of just 100 people, so to speak? I don't know what the average number of people building houses, but suffice it to say that for a single normal family house, right, it's probably somewhere between a couple dozen people and 100. And for large buildings, right, it's probably in the thousands. But if we multiply that number to just add 100 times more people working on this construction site, would things actually improve? And in general, they probably wouldn't improve that much, right? At some point, the site just gets too crowded to work. There's not as many individual tasks that can be done. And every person that you add adds overhead of coordination and communication. And some tasks, right, you just have to wait for something to be done. You can't plumb a house before you have walls. You can't put up walls before you have architecture diagrams and engineering reviews and so on. So just adding more people doesn't necessarily speed up every part of the process. And it turns out that this analogy is almost exactly the same as when we think about the programs that we might want to write. Now in CS10, you probably won't get a chance to write many of these programs, but if you continue on, especially if you get to work on larger systems, if you get to do research, if you go take a job that's related to data science or building web applications, you'll find lots of tasks that have these kind of mechanics. So in general, we could think about tasks though that do break up a little bit more easily. So I'm not going to go through all of these right now, just so we could get through more things, right? But are there tasks that 100,000 people could do? The Great Wall of China is something that we could imagine is thousands of miles long. We could pretty easily add a bunch more people to work on it in smaller segments most of the time. At some point, you need some coordination. So you can't just sort of, you can't add an infinite number of people and have a task be completed in 0 time, practically speaking, but some tasks get closer than others. In some tasks, if our goal is to just make more of something, you can make more noise by adding more people. It doesn't necessarily save you time, but the volume of your output is greater. So if you're just trying to produce more of the same thing at the same time, you can usually parallelize that pretty quickly, right? You can imagine something like an iPhone production facility, assuming you have the parts, which given this is 2022 is a pretty big assumption, but assuming you have the parts and it takes, let's say, 1 day to make one iPhone, you can make, and you have one assembly line, you can make one iPhone a day. You can make hundreds of iPhones a day by having hundreds of assembly lines. In the same way that if you wanted to consume a pizza, right, if you go from 1 person to 8 people, you could each eat one slice in roughly the same amount of time, aside from eating competitions. But there's also lots of tasks where you can't necessarily speed up the process, right? So driving a car, 2 people don't generally drive a car faster than 1 person because only 1 person can realistically be driving at a time. If you're like marathon running things, I suppose, you don't have to sleep, but you still can't increase your speed beyond what's safe or what the car will do, depending on how you look at that. And so the thing to think about here is that some of our tasks parallelize very well and some don't. And we're going to look at how computers handle some of these things. So in general, our goal will be to have multiple computers or multiple processors on a computer be able to divide up the work if possible. So could we have multiple lab computers work together on a single task? In practice, this is a little bit hard to coordinate, but if you continue taking computer science courses, so CS61C, the sort of 3rd course in the sequence, you get to spend time discussing and actually understanding how that communication happens between multiple machines. So we have a bunch of lab computers, they could work together. In practice, what also happens is places like Amazon and Microsoft and Google rent out thousands or hundreds of thousands or millions of computers to people who run websites and other large-scale projects on them. And all those computers that someone rents are working on similar problems all at the same time. So every person that goes to Amazon.com, I don't know how many people will visit Amazon at the same time, but let's say there's thousands of people visiting Amazon every second. You could easily parallelize a process like that to have 1,000 different computers responding to those requests so that everyone gets a result basically instantaneously. Instead of having to wait for the server to respond to one customer, then waiting to respond to another, and then another. When a website goes down and it doesn't load for you, it's typically because too many people are trying to load the website at once. And so if you had more computers, you can generally make a process go faster. So how that happens, we're not going to get into the details, but websites, data computations, certain things like that definitely parallelize very, very quickly. So one thing that we will only very briefly talk about that today, but can a single computer divide up the work amongst itself? And we're going to talk a little bit about how processors and how things work on the inside of insides of computers, because some of these things are just interesting to be aware of, but also fundamentally affect how we're able to use computers. So these next few slides are going to be a simplification and not something you need to fully understand the details of, but just for background, if you're interested on how how a processor works. So every processor is made up of billions of these things called transistors. And technically they have these three things. They have an emitter, a collector, and this base. But basically voltage flows into a transistor. And when the voltage is high, that's equivalent to it being on or a 1. And when there's no voltage, it's equivalent to sort of being a 0 or something being off. And transistors, by allowing voltage to pass through them, are able to represent these values of on and off. And if you think about that, that ends up being how we get binary. That's a pretty high-level simplification. But using these collections of transistors, we're able to build processors that accomplish various kinds of tasks. And one of the things is that every transistor allows us to do sort of one very, very simple computation, on or off, on or off. And billions of transistors allow us to do billions of very simple computations. But when we have billions of computations and we do a whole bunch of crazy stuff that is way beyond the scope of any class that you take at Berkeley, you can actually sort of build a processor that computes useful kinds of information. And so this is here mostly for interest if you want to watch the video. But modern processor technology uses a whole bunch of design software, this really cool process called lithography to sort of print using incredibly precise lasers to essentially print layers of transistors on what is actually the silicon that processors are made of, and to sort of build up a very minuscule 3D version of a processor that has billions of these elements. So you can watch the video after class if you're curious. But when we make these circuits, what modern technology has been able to do is to pack more and more transistors in smaller and smaller spaces. And for us as humans, that's great, because what this means is that over time, our computers basically get faster and faster. And so one of the pioneers of processing in general is Gordon Moore, who is one of the co-founders of Intel. Gordon Moore was a Berkeley, I believe he was a graduate of the physics program in the late 40s or early 50s, because computer science is the department, certainly electrical engineering. These types of things didn't really exist back then, or at least not in their current form. But Gordon Moore is one of the co-founders of Intel, graduated from Berkeley. And in 1965, he predicted that, well, first he observed that the density of transistors had increased from roughly 16 per chip in 1962 to 128 per chip in 1965, which, given that I've said billions are on something like the chip in your iPhone has billions of transistors, this is a pretty astonishing trend. And his observation was that this trend has increased incredibly rapidly. What he predicted was that by 1965, the density of transistors on a chip would increase to 65,000. And when we say density, what we really just mean is more transistors in a smaller area. So that if you have, and I don't know what his exact area was here, but basically, even if you make processors smaller to fit into smaller devices, the amount of transistors that you can pack in one space decreases, or the amount of transistors that you can pack in a space increases over time. The size of each transistor keeps increasing. And most of the technological advances in the past few decades have all been around shrinking the size of the lasers that print chips so that you can print more and more transistors on a single chip. And so what he said is this trend he thought would continue for a long time. And this became known as Moore's Law, that roughly every 2 years, the density of transistors on a chip would double. And it kind of became a self-fulfilling prophecy. If you write software, what that meant is, as a programmer, is that roughly every 2 years, your computer would get twice as fast. And that's not quite what Moore's Law says, but in the early days especially, twice as many transistors meant chips that were twice as fast. And that was a really good thing because it meant that the more software you could write, the faster it would become in the future. That even if you had the same software in 2 years, it would basically run twice as quickly. These same kind of transistors are the things that power the memory on our computer. So if you have 8 gigabytes of RAM or 16 gigabytes of RAM, or maybe even 32 gigabytes of RAM on your computer, that RAM is also made up of transistors. And so the reason that that increases so much over time is because the more transistors we get on a chip, the faster or the smaller we can make them, the cheaper that we can make them, the more processing power we have in terms of things doubling. So we've said that Moore's Law, that the number of transistors doubles every 2 years. What kind of a growth pattern is this? So is it constant, logarithmic, linear, quadratic, or exponential? So take about 30 seconds and I will pull folks in the room and on Zoom for the answer to this question. So if something doubles every 2 years, what is the order of growth of this pattern? All right, so folks on Zoom, if you can just write A, B, C, D, or E in the chat. Anyone in the room, it's not too many today, but anyone want to vote for A? Anyone want to vote for B? Anyone want to vote for C? C. Anyone want to vote for D? And anyone want to vote for E? All right, so we've got a few votes for C in the room. We've got 1 vote for E on Zoom, not too many votes on Zoom. The correct answer in this case is E, that this is an exponential pattern. And if I actually go back over here, this graph is lying a little bit because the scale of years is compressed, where it's not a perfectly linear plot. But doubling every 2 years means that it's not linear. So I need to add, I didn't have time, but I will go back and add a perfect exponential graph. Is that at year 1, let's say we have 2 transistors. 2 years down the line, we would have 4 transistors because we'd double that. And then 2 years after that, we'd have 8 transistors. 2 years after that, we'd have 16 transistors, then 32, 64. And doubling, if we can really take some value and double it every 2 years, meaning we're doubling the previous value, that gives us exponential growth. And that is the reason why over the past, let's say 30 to 40 to 50 years, computers have gotten so much more powerful, is that whether because it was destiny or because it became a self-fulfilling prophecy, the ability to pack more power or more computing power in smaller and smaller spaces in this exponential fashion has made it incredibly beneficial for us to be able to do the kinds of things that we do on computers today. So that one is exponential growth. And what this means is that we get a bunch of advantages. So of course, more transistors in the same space, given that these things are what does the computing, are good. But what it also means is that we can do, we can have smaller chips that run just as fast. So things like smartwatches wouldn't be possible without smaller transistors. It also turns out that we can make, for things like servers and desktop computers, we can make larger processors that have more chips in them because we have more space. And so one of the challenges, though, that comes that we can keep doubling things every 2 years, but processors also hit this issue of what we can call power density or power use. So computers today are incredibly powerful, but what that also means is they use a fair amount of power. And we're not going to go through and look at this entire graph. But one of the things to note over time is that this graph just shows a bunch of things that happen with computers. So they show the number of transistors going up, but that's not quite as interesting. But what they do show is in red over here, is they show the power consumed sort of leveling off. And this graph stops at about 2020. So computers sort of, or computer designers have sort of hit a wall where we don't want to consume too much more power in an individual computer. That's arguably very good for things like energy efficiency and the use of power that we don't want to waste. The frequency or the speed, so if you've heard the term 4 gigahertz, 3 gigahertz, that's the frequency. We're not going to talk about too much. Individual chips stop getting faster, but what does happen is we compensate by doing things like what's in black here, is the logical number of cores, or multi-core system. So instead of having one processor, we now have a dual-core processor or a quad-core processor. Or if you have a recent Apple laptop that's based on their own sort of the M1 Mac, you probably have a processor that has anywhere from 8 to 32 cores on a single chip. And what this does is it changes the game from not just the number of transistors, not just a single processor, but to multiple things going on at the same time frame. And so this ends up leading to concurrency being important in a different way. So just for a little bit of context, over time, we were able to just cram more transistors into a smaller space. And somewhere around the year 2000, the game had to change from individual chips to multi-core chips. So that's loosely what shows up in this like little inflection point right here on this graph. And this is because over time, the amount of heat that an individual processor used, which is so great that we couldn't keep pumping more power into individual processors. And so one way to measure this, obviously this is kind of a funny graph because it doesn't really accurately capture the amount of heat. But if we talk about density, processors are so small that if you measured, whoops, okay, so the animations here are not showing up. But in, let's say the year 2000 or so, the Pentium 6 processor was now a very old and slow processor, but it had about the heat density of a hot plate, which a hot plate produces something like 1,000 watts of electricity to warm an entire thing of food and cook it. If this trend continued, the density of a small chip would approach some obscene things, like the density of a nuclear reactor, which produces a ton of heat, but it's very large. So chip designers basically realized that we can't keep pumping more energy into a chip. And so what they did was, to speed up computers, they went to start designing multi-core processors. And that's where concurrency becomes an issue for us today. So we get more transistors, but we can't run them any faster. If we're still limited by this sort of 2 to 3 gigahertz or 2 to 4 gigahertz number, it means we have to be doing multiple tasks at the same time to be able to take advantage of multiple processors running on our computer. And so today, modern operating systems are less simple than that simplified view, but they allow us to take advantage of multiple processors happening at once. So the good thing here is that we get a bunch of tasks happening at the same time, for essentially one processor. And in some cases, we get a very nice speed up. But the bad part is that a lot of tasks still don't speed up very well. And so we don't get to realize the full speed up. So concurrency itself can be tricky to get right. And so what we're going to think about is theoretically, how fast could we speed up a program? And actually, let me go to the next slide first. This speed up or this theoretical speed up is known as Andel's law. And so we're going to probably finish with Andel's law today, and we're going to talk about concurrency and snap on Wednesday a little bit more, visualizing some of that. But every program that we write has two parts, or we can sort of simplify it into two parts. Something that we could do in serial, something that has to be done in order at the beginning, that is sort of a startup task, and everything else that can be done in parallel that can be split up into as many different kinds of tasks as possible. So Andel's law is, it feels a little bit complicated, but it's a relatively sort of simple equation, which is what is the maximum speed up that is possible for our program? And if we have one processor, then we don't get any speed up. But if we have two processors, we get some amount of speed up. If we have three processors, we get more speed up. And what Andel's law says is we have to separate out a program into two parts, a serial part and a parallel part. And our maximum speed up is determined solely by what percentage of our program is parallel and how far can we speed that up. So the real way that this is written out is our total speed up is 1 over the percentage of our program, or I should say it's roughly 1 over the number of processors. So what percentage of our program can we, actually, let's go back to this. The way to think about Andel's law, let me start that over because I started reading P the wrong way, is given a number of processors, the speed up that we can achieve is 1 over the number of processors in theory, right? So if we have 5 processors, we can in theory achieve 5 times speed up if our program is 100% parallel. If our program is 100% parallel and we have 5 processors, we could theoretically speed up our program by 5 times. But in practice, we have this serial portion. And so we have to subtract out our serial portion. In our formula, it shows up as, I'll go back to 1 minus s. And if we have 1 minus some serial portion over some number of processors, how much faster can we make our program? And Andel's law gets us to gets us to think about what if we had an infinite number of processors? What is our theoretical maximum percentage that we could speed things up? So we're going to do one example of this, and then I'll take some questions. So I'm going to walk through this because the math is simpler than it sounds if we just sort of break this down into parts. So if we have 20% of our program is serial, so if the first fifth of our program has to be done before the remaining 4/5 of our program, and we think that we have an infinite number of processors, what is the maximum speed up that we could achieve inside our program? So this question is sort of the heart of how we think about building parallel, or how sort of programmers can think about sort of building programs that are parallel. So if a fifth of our program, if a fifth of our program is serial, the remaining 80% can be done in parallel. What is the maximum speed up that we could achieve? So this assumes that we have an infinite number of processors, which in practice is not really ever going to be the case. But if you have the ability to, let's say, contract out to Amazon or Google and buy some cloud computing, you actually have pretty close to an infinite amount of processors. So how much speed up could we realistically achieve in this example? The nice thing about an infinite number of processors is that we can assume that 80% of time that it takes can be done instantaneously. So if I can assume that 80% of the work can be done instantaneously, then the maximum speed up that I have is limited purely by this serial portion of our code. The part that needs to happen before the rest of our code, which would mean 1/1/5 of our code, would be a 5 times speed up. So if we have a 5 times speed up in our code, or excuse me, if we have 1/5 of our code is serial, then the maximum speed up with an infinite number of processors is 5 times. It should just be 1/1/5. I'm going to do a couple more examples because the formula on here got a little messed up, so it's a little bit less clear. But yeah, so any questions so far on this idea? I know that today was a little bit fast for lecture, but questions on this idea of parallel and serial parts. We'll come back to this on Wednesday. Yeah.
Could you explain again why we use that formula?
Yeah, so the idea here is if I have half my program, or let's say a fifth of my program, whatever it is, that has to happen before some other part happens, then I have to split up the problem into essentially 2 parts. What has to be done first, that has to happen in order, versus what can happen in parallel. And Amdahl's law lets us say, by separating a program out into these 2 ways, I can reason about how much speed up I can get overall from the portion that happens in parallel. Now, in a program that we write, it can be really hard to reason about what needs to happen first versus what needs to happen second or third or in parallel. And so in some cases, you might think about, like, if we're processing a bunch of data, right? The first step that I need to do is download and load in all that data. And I can't do anything until I have that data on my computer. But once I have that data, I can probably I can potentially at least split up some of the tasks into multiple parts. And so that's the reason that we break this down into a serial and a parallel portion. On Wednesday, when we talk about sort of some of the limits, I'll spend a little bit of time referencing things like our map and combine blocks, and why, if we do functional programming, we actually get to take advantage theoretically of some of these tasks a little bit more easily. But yeah, we'll keep working on this on Wednesday. So if there's any other questions, I'll take them, but it is noon. So we'll see you on Wednesday. We'll wrap this up, and then we'll have just one more topic of CS10.
Thank you.
Thanks. Thanks everyone on Zoom.